Now, diodes are active power semiconductors that can block a voltage or short circuit two nodes dependent on the current going through it. But there is no other way of controlling it other than the voltage and the current. But to achieve our goals of building power converters, we want to get a handle on the power semiconductors and control their behavior. Therefore, we use transistors. More specifically, we often use power MOSFETs. MOSFET stands for metal, oxide, semiconductor, field effect, transistor. Now, the metal is often represented by the gate, which used to be actually metal. Nowadays, it's more highly doped silicon. The oxide is in between the gate and the channel, and that is what is defining the node of the actual process that you're using. So if we're speaking about a 7 nanometer process, 7 nanometers is the thickness of this oxide. Now, power devices for hundreds of volts are more up in the sub-micrometer range than down in the nanometer range. The semiconductor is very important on the channel, which is mainly the drain and the source and the connection in between them. And the field effect is the field across that channel when it's blocking. And at the end, we end up with the whole thing, which is a transistor. That explains the abbreviation MOSFET. Compared to the diodes, where we also had a blocking voltage, here in terms of MOSFET, it's called the drain source voltage. And we have a power current, which in terms of the MOSFETs is the drain current, coming mainly out again on the source. We also have a third pin, which is the gate, having also a gate current and having a controlling voltage over the device being VGS. The characteristics of an ideal MOSFET are either conducting, which is conducting in both directions, so it can conduct positive and negative current, or blocking, which means only positive voltage can be blocked by the MOSFET. Negative voltage would be short-circuited out by a parasitic element called the body diode, which is connected with its anode on the source and its cathode on the drain. A simple symbol to quickly represent a MOSFET in a circuit diagram or in a sketch is to use a simple switch. Now, the ideal MOSFET was operating only along the y-axis in both directions or blocking voltage along the x-axis, but never leaving the axes. That means you either have voltage or current, but never both at the same time. That means you don't have any losses in them. Practically, the operation of the MOSFETs cannot reach the axes, and we are more like somewhere on a straight line, which is controlled by the gate source voltage. And the lower the gate source voltage, the equivalent on resistance, which is the derivative of this straight line in the ID characteristics of the MOSFET, are dominating the losses, and it can be modeled as a controlled resistor or also a potentiometer. The controlling voltage, the controlling signal for that potentiometer is in that case the gate source voltage, and the higher the gate source voltage, the lower the RDSon, and therefore also the lower losses we would get, because we actually get closer to the y-axis where we ideally want to operate the transistor while it is conducting current. For the modeling of the off state of the MOSFET, it is actually pretty adequate to assume that we are really close to the x-axis of the IV characteristics, which is good enough for the rest of the course. As we have used a three-stage modeling principle for the diodes with the ideal and the simple model of a diode, We also can use for the MOSFETs a third one, which is getting closer to how the MOSFETs actually is really behaving, and have a look at the datasheet of one of an example of a MOSFET. IRF is an abbreviation of the manufacturer, in this case International Rectifier, who originally designed this MOSFET, and the type 550 is actually a rather traditional power MOSFET, but still very active and actual MOSFET. The company meanwhile got bought by another company called Infineon, but the transistor IRF 540 is one of the examples that got also produced by a number of other vendors and therefore can be found on the internet from different suppliers and different manufacturers. Now let's jump straight into the datasheet. Here we are looking into the first page of the datasheet with its most important values defined in the upper right box here, which is the drain source voltage this device can withstand, which is 100 volts, and an RDSon of 44 milliohms, and a maximum drain current it can conduct of 33 amps. Now, as we will see in a second, the 44 milliohms is only one data point on a graph that can be varying a lot. The device is produced and shipped in a package again called TO220, which is a very standard package for those kind of devices. The next section is about the absolute maximum ratings, and then something about the thermal characteristics of the device that we're gonna look later into in the course. Now moving on to page 2 of the datasheet, we have a table called the electrical characteristics. The electrical characteristics table is telling us quite a lot about the operation of the device in a converter. The numbers here are specified for a junction temperature, so the silicon temperature inside the device of 25 degrees Celsius, which is a de facto standard for room temperature. The 100 volts of drain source breakdown voltage is given as a minimum, so we have a guaranteed blocking voltage of at least 100 volts. The 44 milliohm are given at a maximum for these operating conditions, then 16 amps through the device, which is not the maximum the device can actually conduct, and a control voltage of 10 volts. The gate threshold voltage is telling us when the device actually starts to turn on to conduct the current. And note that this parameter has a rather high relative tolerance, being specified somewhere between 2.0 and 4.0 volts. So if we assume that the average of this is 3 volts, we actually have a tolerance of about 33% of this parameter, which is rather huge. Moving on to the diagrams of those parameters and observe how that looks when we're actually starting to scale some of those parameters. First of all, the IV characteristics of the device. This is equivalent to the diagram that we have been looking at in the ideal and in the simple modeling case on the slides. Here, one of the diagrams is given for the junction temperature of 25 degrees, and the other one models the behavior of the device at a junction temperature of 175 degrees, which is a maximum value for the device, but it's still realistic that the device would actually operate somewhere between 100 and 150 degrees C at its maximum operating temperature. Note that the linear operation characteristics easily can be represented by straight lines in both cases. However, these are straight lines on a double logarithmic diagram. So the drain source current in amperes is in a logarithmic scale, as is the drain source voltage of the device. The different lines represent different gate source controlling voltages from bottom to top, starting at 4.5 volt, so slightly above the gate threshold voltage of maximum 4 volts in both cases. Note that the saturation characteristics are rather different at 175 degrees compared to the 25-degree case. Moving on to the next two diagrams in the datasheet tells us on the left-hand side about the control characteristics of the device, starting with the gate source voltage, the controlling parameter of our potentiometer in the simplified case on the x-axis, and that one also starting at the threshold voltage maximum of 4 volts. The transistor starts to conduct significant current right above that, but to be in a fully on state, as we are using it in the terminology of power electronics, we would ideally like to operate at least up here. The right-hand side diagram is normalizing the on resistance of the transistor, as we have seen from the first page of the datasheet, as 44 milliohms. So the normalized factor of 1.0 represents the 44 milliohms that were also represented in the diode of the electrical characteristics of the MOSFET. Interestingly, we can see here that the 44 milliohms are true for a junction temperature of about 25 degrees C, which again is a de facto standard for room temperature. But at higher operating temperatures, let's choose a realistic one of about 120 degrees junction temperature, we actually end up with twice the on resistance, so we actually have 88 milliohms at that temperature. Now, even though the electrical characteristics table said that it is a maximum of 44 milliohm, we also need to take into account under which conditions this maximum was specified, and look into the graphs of the datasheet to read out the operation point where we are actually using the device in our specific converter. Another condition for this diagram is that the drain current is 33 amps, which is the maximum of the device, and the gate source voltage, the controlling voltage, is 10 volts. Note that these 10 volts are actually outside the scope of the diagram on the left side. On the next page, we can find information about other parasitics of the MOSFET. Between each of the terminals, gate, drain, and source, you can find a parasitic capacitor. That is the gate source capacitance, the gate drain capacitance, and the drain source capacitance. Combinations of these three capacitances, according to the equations on this diagram, result in the input capacitance, the reverse capacitance, and the output capacitance of the device, which end up to be highly nonlinear across the drain source voltage. One more highly nonlinear characteristic of a MOSFET is represented in the right-hand side diagram. The total amount of charge in the gate is plotted on the x-axis, and the gate source voltage, the one controlling our device, is plotted on the y-axis. We had the threshold voltage of the device between 2 volts and 4 volts. Above that threshold voltage, we can see the so-called Miller plateau of the device. That Miller plateau is defining the voltage blocking characteristics across the field effect, across the drain source connection of the device, of our power transistor. Now, with the extracted information from the datasheet, we can continue our modeling of the MOSFET operation in converters. We are especially interested in the loss mechanisms of a power MOSFET. As in the case of diodes, a MOSFET has conduction losses and switching losses. And as the MOSFET has a third connection, it also has gate drive losses. The conduction loss mechanism is similar to the one as we've experienced from the diode. While the power device is conducting current, its resistance is not zero. So we have the finite on resistance of the MOSFET and conducting the drain source current through it. We can take the RMS value of that current, square it, and calculate the conduction losses of the MOSFET with the equation 49. For modeling the gate drive losses, we represent the power MOSFET through a potentiometer, which has its control pin, and especially we include the input capacitance that we can extract from the datasheet diagram over here. Note that this parameter is somewhat nonlinear over the drain source voltage of the power MOSFET, and we need to operate it at the specific operating point that we are using. Now, a gate driver is typically another IC, another integrated circuit, which has its own supply represented by VG here. And the output stage of that gate driver is very often a totem pole configuration with a high side device and a low side device. Whenever we turn on the power MOSFET, we conduct current through the high side device in the gate driver, charge the input capacitance of the MOSFET, and that current returns to its source. For turning off the power MOSFET, we retract those charges into the low side of the totem pole driver and burn the energy in the on resistance of the low side transistor in the totem pole configuration. Now, these switching instances result into gate losses represented by this equation and through the nonlinear characteristics of the power MOSFET represented in the graph in the upper right hand of the picture. We can transfer that into half of the gate charge times the gate voltage. And note that these losses actually occur in a power converter twice: when turning off the power device, as noted here by the red illustration, and again by turning it on, as was indicated by the blue illustration in the upper circuit diagram. Now, the third switching loss mechanism is similar to what we had in the reverse recovery losses in the diodes, but where the reverse recovery losses only occurred when the diode was changing its stage from conducting current to blocking voltage. We have the switching losses in a MOSFET, again, both a turn on and a turn off of the power device. Now that we have modeled the gate drive through a capacitor and that we know that the totem pole stage of the gate driver can be represented as a resistor, we can model the turn on waveforms as an exponentially rising gate source voltage until we reach the Miller plateau. On the way to the Miller plateau, we cross the threshold voltage, and at the threshold voltage, the drain current of the device starts to rise. That means the transistor starts conducting. When we reach the Miller plateau with the gate source voltage, the drain source voltage stops blocking the reverse voltage, the voltage that was applied across drain and source. At the end of the Miller plateau, this process is finished and the voltage across the drain source collapsed all the way down to zero. At that point, we reach the steady state, and we continue conducting current through the drain source. The gate source voltage is way above the threshold voltage, and the device is considered fully on until we reverse the cycle. When we are starting to turn off the device, we first reach the Miller plateau. That means the transistor starts blocking the voltage while it is still fully conducting the current, as seen by the orange waveform down here. First, towards the end of the Miller plateau, the drain source current starts to collapse, and first when actually reaching the threshold voltage on the way down through the exponential functions, the conduction time of the MOSFET is over, and we are fully blocking the voltage while not conducting any current anymore. Now, during the steady states, we either have zero voltage across the device and the desired current flowing through it, as indicated by the blue lines here, or we have the device blocking the voltage and conducting no current at all. That means it is off. The state where we have full current through it and no voltage across it is often simply called on. But during the transitions, both of them, the turn on and the turn off transitions, we also have states where we have both voltage across the drain source and current through the drain source channel. And having both a voltage across a resistive device and current through it means power losses. These losses are represented by the areas where we have voltage and current simultaneously applied to our MOSFET, indicated by the red area for the turn on and indicated by the red area as well over here for turn off. Now note that these areas are not looking exactly the same, which is based on the shape of the exponential functions from the gate control. You can find the simplified equations for those losses in the textbook.